Well, thanks to the organizers for inviting me. It's lovely to be here. Um, so I guess so what I'm going to talk to you about is about error analysis in, let's say, DMD or EDMD or this kind of thing, eigenvalue problems in general. So, and in particular the spectral analysis, spectral error analysis. So we imagine, I mean, perhaps this is how you could think of it. We're trying to approximate our Koopman operator, and we're given a finite amount of data that we can use to do this. We have a finite dictionary size with which, set of functions which we can do this, and we do some kind of least squares approximation that Carl sort of briefly explained to you, and you have, I'm sure, seen many, many times to get some sort of matrix, which I'm going to call K hat. And this is going to have some sort of spectrum. And then the hope is that, the idea is, I guess, that as you increase your number of data points, you end up at some kind of limiting matrix, which is what you're going to get if you do a kind of least squares approximation with respect to the kind of the sampling measure of wherever your data is coming from. This will give you some matrix K, and I guess in many cases this has a slightly nicer sort of set of spectrum, but it's still a matrix. And then the final thing that you hope to do is to increase your dictionary size, off to infinity, to recover maybe L2 or just recover a large enough set of functions so that the eigenvalues of this will turn into some kind of limiting object, and the kind of, let's say, the discrete eigenvalues of this problem look like kind of correspond to items of dynamical information. So I guess this is maybe a recipe for uh, dynamical systems study. So where I come from is actually I come from a sort of chaotic, sort of pure chaos background, we could say. And in sort of pure chaos world, we study these kinds of similar operators to Koopman operators called transfer operators. And basically, one thing that you can do is try and study how the eigenvalues of like these eigenvalues for some sort of limiting matrix here, which you can, do various constructs on your computer, how this converges to what we think of as the spectrum of the Koopman operator, which is not necessarily a spectrum in L2, but a spectrum in some very carefully constructed Banach space, in which basically you get these discrete eigenvalues that have some kind of canonical significance to us. And so, I guess there's some recent, I guess, work which is sort of saying that the kind of eigenvalues you get in this limiting matrix setting look like these eigenvalues that you get in the kind of canonical sense. That's not actually what I'm going to talk about. So this talk I kind of want to sort of talk about partly because it's, we know that there's no one answer to what's going on here, but here it's a bit easier to deal with. So yeah, I want to talk about kind of quantifying this kind of error in particular and how the kind of your matrix errors in your matrix turn into errors in your spectrum. So okay, yes. So this is kind of our question, that we have some kind of finite amount of data with which to work in. How can we actually test for the spectrum of this infinite data matrix, which we hope will look like the spectrum of something like a spectrum of our true Koopman operator. And of course, there are problems with these. The kind of matrices we get are usually quite non-normal. So, they're not unitary, they're not symmetric, something like this. The kind of thing about this is that the eigenvalues tend to have different amounts of stability. It's not easy to predict how stable to perturbation they are necessarily. So we can see here are some peripheral eigenvalues, and some of them, if I take, I've taken 20 realizations of computing a database EDMD matrix and taking its spectrum, we can see that they're very close to the kind of infinite data limit. Some of them are less close. In fact, and then we have this kind of cloud of eigenvalues in here, and you can see that when we take our database approximation, it's not just that they're clustering around the particular eigenvalues, they actually kind of expand outwards a bit. So, here is a bunch of stuff that we probably, have seen before, but we couldn't, if we wanted to get a computer to tell us that was happening, we might not know how to get it to do that. So what I want to talk about really is a sort of, let's say, a statistical test to kind of guess whether this is going to happen, what is actually going to happen in the context from the data. I mean, I say guess, I mean, guess with theorems. So I guess I'll just talk about my setup here. So we imagine that we have this matrix K, which we sample, which we create by some DMD, EDMD, getting with regularization, whatever. We imagine it's sampled from some set of data points. So I've sampled some XMs and I've computed f of XM. And I hope, as Carl was sort of talking a bit about, we have a an ergodic distribution here. So as basically over the long run, if I take a lot of, average some function over XM, over the long time, if I increase my data to infinity, it will converge to some sort of expectation with respect to this distribution. And there are many ways we could do this. We could do just independently sample a bunch of points against some measure that kind of hopefully will be useful to some sort of measure that we then construct a Koopman-Rowan operator against, or we could sort of sample it against dynamics. So we could run, say, an SDE for a long time. It will have some ergodic behavior. And then, well, somehow if we run it for long enough, it will start to converge these expectations. What's interesting is we can also do this in many chaotic systems. There are kind of sort of physically relevant invariant measures where if we run our system, if we think of this as f to the m of x, we run it for a long time, these averages will also converge. So here's a picture of that. And well, in many of these scenarios, we kind of know that the convergence of, let's say, elements of my Koopman operator or elements of my cross-Koop gram matrix or whatever will converge as order 1 on root m. And therefore, as Milan and Igor pointed out, this means that everything else is going to converge as well at this same rate because we're in a finite dimensional world. Of course, we don't know what the constant in front of this is necessarily, so that's kind of a lot of what I want to talk about here. So many, I guess, and it's worth noting that this is not just true of, say, SDEs or independent sampling, it's also true of a lot of chaotic systems, fluid flows and all this. Even if they're deterministic, we get a kind of central limit theorem where if we take out our mean and we normalize it appropriately, we get convergence to a normal distribution. And we can estimate this variance using what is in some places known as Green-Kubo formula, which is basically a bunch of cross correlations. You kind of expand out, the variance of this guy, and you will get, well, you get at least formally an expression of this if you take the limit. And it looks a bit nasty because it's an infinite sum of some things that maybe you want to approximate by Monte Carlo, but it is quite possible, let's say, to construct estimators of this guy that are, asymptotically accurate as we take data to infinity and also stay positive, as you would hope a variance to do. Okay. So how does this? What's the kind of DMD and this or EDMD? So we imagine that we have. Let's just start by assuming that our data size, the number of data points we have, is bigger than the number of observables. Specifically for DMD or EDMD, we kind of need this for invertibility. And imagine we're doing some sort of exact thing where we have an invertible gram matrix. So our Koopman operator estimate with our finite data and our finite observables is, well, I think usually we write it the other way around, but I've sort of written it this way because I've just written it this way. So it's basically an inverse of this gram matrix times this kind of cross-correlation matrix. And, well, okay, as we take our data to infinity, we get some ergodicity here. So we end up with an expectation with respect to these points, with respect to these functions here. So this psi star is a matrix, and we're taking an average over it. So we're going to converge to an average of one average of all of these, which is also an expectation of the G itself. And similarly for this A. We have these possibilities. Okay, so so this is a bit annoying really to think about it. So it's a bit annoying to think about the convergence of our Koopman operator because we have to take the inverse of something with respect to something else. So this is quite nonlinear. But if we're worried about the spectrum, right? So lambda is an eigenvalue of this k hat. If for some vector v we have g inverse a of v is equal to lambda v, but we can multiply both sides by g. So this is the same thing as saying that this kind of, well, we'll call a characteristic matrix has v as its kernel. Okay, if you've seen some res DMD stuff, this is kind of similar areas. Okay, so kind of our test for an eigenvalue for some complex number lambda being an eigenvalue of our data-driven Koopman matrix is basically just that this matrix here, this c hat lambda here, has a kernel. Okay. And of course, what is C hat lambda as we take m to infinity? Well, it kind of turns into it approaches its expectation by the Birkhoff-Egonoff theory. So, or, by Oganesky. So this is just kind of a, you know, take m to infinity, and we approach this. So what we're sampling here with this characteristic matrix is kind of like a, yeah, it's kind of an unbiased estimator of this. And okay, just good to note that this characteristic matrix is itself a kind of expectation of some rank one matrix function of observables of a sample. So yeah, basically our test is what we really want to test for is given that I know this C hat of lambda, is my true C of lambda, is my true C of lambda equal to 0? Or does it have a kernel? A non-zero kernel, right? That if this holds, then we have lambda is an eigenvalue of our infinite data matrix. So yeah, kind of we want a statistical test for this. And well, this is somehow, does a matrix have a kernel? Bit hard to say, but if we start with a one-dimensional case, we might pick up some ideas, right? So the one-dimensional case is something you will have learned in first year statistics. It's just a t-test. And I've squared my statistic here because it'll be useful later on. But what we basically do is we take the ratio between we take sample mean, we divide it by its sample standard deviation, we normalize appropriately, because the sample mean will be as a Bayes' central limit theorem. And we decide that if this thing here, well, if our true mean of our sample is equal to 0, then, well, our sample mean here is going to be something like normally distributed with variance close to the true variance, so this is basically going to become like a t-distribution, which is good enough, or the square of a t-distribution because I've squared it. So it's good enough as saying it will be distributed like the square of a normal random variable. Okay, on the other hand, if my true mean is non-zero, then my standard sample mean is going to converge to the true mean by the law of large numbers. So this is going to become a constant. This becomes a constant. And as I take m to infinity, my m here stays here. So this is going to grow at a kind of linear rate. So I kind of have this kind of dichotomy here. If my mean is 0, then I stay bounded. If my mean is non-zero, then I grow linearly. And this lets me do a statistical test because I can just say, well, if the mean truly is 0, then this should be distributed like a square of a normal random variable. And I can just figure out what the probability of this thing is. Okay, so the hope is to do something analogous for residuals, these residuals. So, and if we know exactly what our V is, we're going to say, I know that this might be an eigenvector. I'm going to test to see whether it's 0. We basically want to test whether we're given C hat lambda of V, right? This is something we can get from our data. And this is an estimator of C lambda of V. So if this guy is 0, then this guy should be small. So I'm going to take the norm of C lambda of V to get myself back into scalar world. And I'm going to divide by something that looks like a sample variance of this guy. Okay, so at this point, I should just say we're trying to keep it general. We don't want to necessarily specify a specific norm on my matrix because I don't necessarily know what the best norm for it is going to be. Well, I just want to keep my options open, really. So any Hilbert space norm we can write in this form. So A star QA for some positive definite matrix Q. So yeah, this is like one-to-one relationship between Hilbert norms and positive definite matrices in finite dimensions. And yeah, I'm going to say that this guy here estimates basically like my variance of this kind of V, C hat lambda applied to V. So that's its expectation, and then I take a norm. So as I take m to infinity, I could think about what the expectation of this is, just as a sort of first guess on like how big it's going to be. And I see that, well, if my true C lambda V, basically my true residual of my vector is not equal to 0, then this is going to converge to a constant. This is going to converge to a constant, and we're going to get that growth as order m. On the other hand, if this true value is equal to 0, then this thing here, C hat lambda of V squared, is going to decay as order 1 on m because it's like the central limit theorem. And yeah, so this thing m times C hat lambda of V squared is going to be order 1. And then we divide by a constant, so it's going to stay of order 1. And in fact, you can show that the expectation of this thing should converge to exactly 1. So again, we have this dichotomy, right? The problem for us is that, well, we're trying to find, we don't actually know what our true eigenvector here is a priori. So this is a true Koopman eigenvector, but it's also the true kernel of the characteristic matrix because they're just little linear transformations of each other. So one way we can fix this is we can take our test statistic, this guy here, and then we can say, well, minimize it over all vectors. Because if our V is truly, if there is like some of these V's, will not be in the kernel of C lambda, so these guys will be big, but there will be one, our true eigenvector of the Koopman operator, where this thing here is small. And so if we minimize it, then we'll pick up that smallness. And the next thing we kind of want, so there we go. We have some statistic, and this should work for us, but we've left Q unfixed. And one thing about this is that, we'll get, I'll just go back, we'll get this kind of dichotomy for any Q, but this constant out the front of n, the rate of growth of my test statistic, if I've chosen M to be, so if I've found, if I'm not at an eigenvalue, the rate of growth of this test statistic here depends on this Q. So I'm going to try and maximize this because then I will maximize I will maximize the power of my test. Basically, the rate of growth will be as big as it possibly can, while if I am truly at an eigenvector, this will stay of order 1. Okay, so this is the test statistic that I'm going to use. Well, I guess it's probably good to say how it, it's probably good to actually say what it is, how you can compute it. And I won't go too much into that, but suffice to say that it is actually something you can compute via a kind of iterative method. And you can do it really quickly, actually. So you just kind of need to have some way to estimate this sort of variance. And, as with one-dimensional cases, it's like the central limit theorem parameter, like the kind of variance parameter, you can do it. It is not too complicated to do. So the kind of mathematical result we have is sort of under some reasonable assumptions I should have put here, is that, again, we have this dichotomy. So if we take some lambda, complex lambda, and it's not in the spectrum of our of our infinite data EDMD matrix, let's say, then as we increase, if we take our data-driven approximation, our finite data approximation, we can compute this from finite data. If we increase m, then this thing here is going to keep growing. It's going to grow linearly according to m. And actually, what's kind of nice is that this parameter here, this constant out the front, m star lambda, pops up, which kind of tells you how much data you need to be able to, sort of confidently assert that and sort of reliably see even that this is not an eigenvalue of your data-driven operator. So it's the amount of data points necessary to see the non-eigenvalue nature of this lambda. So that's one possibility. But the other possibility in our dichotomy is that if lambda is an eigenvalue of k, and so I can prove to you that under some reasonable assumptions, which is sort of mostly to do with positive definiteness, that this that basically we can do it. We have a kind of bound on our distribution of P of lambda. It's going to stay of order 1. And it's basically distributed according to, let's say, a normal distribution or a chi2, like half a chi-squared distribution with degree 2. So, basically either a square, either, I think for this tail here, this is kind of like this bound on the value of P of lambda. And I've looked at a bunch of different true eigenvalues of some EDMD approximation. And you can see that this bound here is basically the distribution of this of a normal distribution squared, and this here is this higher bit here is the distribution of a chi2 squared variable, which comes from the fact that when you compute spectrum, it goes in two directions. It goes in in the imaginary and the real direction as well. So we can actually this is a theorem, and we can use it actually to test where our true spectrums lie. So here I have I think my green points here are some data-driven eigenvalues. So finite, I think I talk about 2,000 values of m. This is some chaotic system. The red are the true eigenvalues if I take m to infinity. And you can see that so I've taken a bunch of different realizations. In each case, my sort of p hat lambda kind of as a function of lambda looks different because I've just got different data that will give me different answers. But in all cases, we can see that the green crosses, no, so the red crosses tend to be in regions of low p hat lambda. So, this is, and that, yeah, this is kind of what you would expect, and it's a fairly tight fit around them. So somehow what we can do is we can, we can sort of figure out if we have some eigenvalue, some green eigenvalue, we can sort of test to see if there is likely to be a red eigenvalue nearby as well. So there's somehow a kind of counting problem here, where if I look inside a ball, a sort of level set of small, let's say of small p hat lambda, then the number of eigenvalues inside each of these sets should be the same for both the red and the green. And there's some maths sort of to kind of the waves. I've got the ways it hands at it, although it's a little bit why it works exactly like this is a bit unproven. But we can sort of use this to distinguish, let's say, real data-driven eigenvalues from ones that are probably just, artifacts of finite data sampling. So, for example, we can always see that there are two eigenvalues to the left here, and these are probably, these definitely correspond to the red ones. Two green ones definitely correspond to two red ones, but the correspondence between the green and the red inside these central blobs is a lot more questionable. And so probably if we look at the eigenvectors, they're probably all interacting with each other when you do the perturbation. And so the eigenspaces let's say, of all of these ones here are all going to be mixed in with each other in a way that maybe we can't necessarily untangle from finite data. So as an example, although there's probably not much time for it, I simulated some Rayleigh-Bernard convection, took some observables, so a kind of EDMD with a delay in it, or maybe it's really just DMD. Took 2,000 data points at a certain sampling interval, which didn't actually capture all of all of the dynamics here, because there's a sort of slow, sort of, I guess, symmetry reversal thing going on. And well, I computed this p hat lambda thing, and I got this kind of, if I did the log transformation on my Koopman operator spectrum, I got this kind of picture here, and you can see that here are some eigenvalues that lie in their own region of low p hat lambda. So we could expect that a true infinite data limit eigenvalue is going to be, there will be one in there, one in there, one in there. There may be a few in here corresponding to the number, although because these are not very well separated, the chance that these are actually connected to mixed in with, say, 6 is mixed in with 18 and 12 is quite likely. And then these guys here are all sort of a jumble, and probably if you looked at the true infinite data eigenvalue, they'd all be kind of somewhere else. They wouldn't bear much relationship to where these ones actually are, because they're all in a region of low p hat lambda. And what we could see is that these eigenvalues here pretty clearly correspond to some patterns in the some sort of periodic behaviors or quasi-periodic behaviors in the cell, which I won't bore you too much with. But then if we looked at, so these ones are good, okay? Because they live in these cells, these places here. But these ones, if I look at 632, which are all kind of jumbled together, they appear to, well, they sort of kind of tend to correlate with each other. And if you look at what they pick up, if you look at when your eigenfunctions are kind of activated, they tend to be picking up the same kinds of things. So they're kind of linearly related to each other. They're sort of all linearly mixed in with each other. And if I took my data to infinity, I think I would find that these would separate out in a way that was these would all look different. So I guess as a conclusion, this is a very effective method to test for the reliability of these eigenvalues. Well, to test your data, right? You have some data, you do EDMD on it, you do DMD, you do something on it, and you want to see if your eigenvalues are artifacts of finite data, or if they're a bit real. And this is a very good way to do it. I don't think it's optimal. I think there's maybe a factor of 2 that you could improve it by. But it does work on, I mean, it is very general. It's just something about linear algebra and random sampling. So it should work on any kind of generalized eigenvalue problem you have. So if you want to put a regularization term in, for example, that'd work. it's pretty low. It's more computational cost than just doing DMD, but it's not very much because you've got to do it for each lambda, but it's not very much. Um, and yeah, so I guess that's kind of, I think it's cool. And if you would like to use it or talk to me about it, please do. I thought I'd have it on the archive, but these things never happen. So yeah, so thank you.